This week, we're going to talk about how to determine if a particular section is adequate. And in part, this is going to follow the mechanical rules that we've talked about so far. And in part, it's going to deal with some of the human-imposed rules we put into the system for safety. And so we're going to look and start to drift a little bit further again away from the scientific application of pure science, because we have to use engineering judgment. And one of the things that we do is we decide how much risk we're going to take, and that risk management is an engineering contractor activity. The science doesn't help us out. So we've been talking about beams, and what we have up on the screen is a beam. The beam has a load somewhere on it that's causing it to bend down, so to form a concave shape, to what we call a sagging moment that causes the beam to sag. Do you remember what the other one is called if it causes the beam to mount up? Is a hogging moment, because it looks like the back of a hog. Engineers, pretty simple people. So it's causing a sagging moment. And what that sagging moment is doing, in our cross-section here, the beam is B, depth of the beam is H. There's a little bit of steel down here. The steel is at a depth of D. It's causing a strain in compression at the top of that beam, and it's causing a strain in tension at the bottom of that beam. Now, we know we made three assumptions. Let's do it the easy way. Number one, that this strain from the top to the bottom is linearly distributed, and that there exists somewhere in there a point where it has to be zero, which is the neutral axis. Our depth to the neutral axis is C. If this was a wooden beam or a steel beam, we would be able to assume, because it doesn't crack, that the neutral axis is in the middle. But that's not true in this case. In this case, the neutral axis is wherever it crosses zero. So we have to make our next assumption. That assumption is very simple. Concrete is unreliable in tension. And the way that we say that is, the tensile strength of the concrete is nil. Null, zero, whatever you want to call it. There isn't any. That's a lie. We could go out into the lab right now, take a beam, bend it. We would find out that it takes some force, not a lot, but some force to crack it. So this is an assumption. It's a safe assumption because we don't know where the cracks are going to be. But we know they're going to be somewhere, right? So how much load can you pass across a crack? Here, we'll do it social distancing wise. Ready? Hold out your hand. Now pull me towards you. Yeah. What happened? Nothing. No force. Can't pass force across a crack, right? But, so we are not going to be able to carry any load in our beam. However, if I take this solid steel bar, now pull me towards you. Right? Not too hard, man. I'm that old. Very good. Yeah, probably is. Don't use me as an example again. Okay. So the steel can carry tension. So we're going to assume that down below the neutral axis, the only thing that's carrying tension is the steel. And the steel has a force in it, and that tension force, capital T, is equal to the area of the steel multiplied by the stress in the steel. We're also going to acknowledge that once the steel has begun to stretch in a permanent fashion, which means it's yielded, it is a strain higher than its yield strain, or it's yielded, that the stress in the steel is known, and that the stress in the steel is F sub y, the yield stress, which almost all the time, for our purposes, is going to be 60 KSI. Just the same way that the compressive strength of the concrete most of the time is going to be 4,000. We'll talk about how we get around that and what we do when we have different strengths. But for right now, that's where we are. Okay? So those are our three assumptions. This is the model that we have constructed. Based on all of these assumptions, we know that the tension force is the area of the steel multiplied by the stress in the steel. And we know that compressive force is carried entirely in the concrete. We also know something, right? If we had forces had imbalanced loads, what would happen to them? If there was more force in tension or more force in compression, it would go flying across the room like that pen did, till it was able to put some load into the floor and stop itself. Right now, it's at static equilibrium, right? There's a gravitational force pulling it towards the center of the earth, and there's a resistance of the slab saying, not so fast, right? So in this particular case, we know that our compression force has to be equal to our tension force because the sum of the forces in the x direction have to be equal. So the compression force, and remember we use this little prime only that it doesn't get confused with that C, right? The depth of the neutral axis. So we know the tension is equal to the compression force. And we don't know exactly how those stresses are distributed in the concrete. But we're going to now say, well, that's okay, because we're going to make the Whitney stress block assumption. The Whitney stress block assumption is that the compressive force is equal to 0.85 F prime C AB, where B is the width of the beam, and A is beta 1 multiplied by the depth to the neutral axis C. And for 4,000 psi, beta 1 is also equal to 0.85. Okay? So for 4,000 psi, we know the compressive force is given as 0.85 F prime C AB, and A is a discounted depth to the neutral axis. Beta 1 is going to be less than 1. So that's an assumption. Is it true?
We don't know it.
No. We know it's not true. But let's suppose that you're going to buy a sufficient amount of soda pop for all of your friends that come over. Okay? After they've drunk some soda pop, they become belligerent. You know, might not be soda pop. You can fail in one of two directions. Which directions can you fail in? What's that? No, but that's good. We're just talking about soda pop. You know, Coors Light soda pop. You can have too little, or you can have too much, right? In an ideal world, you want to be dead center so that everybody, once you've done all your case races and everything else, certainly it's a word I learned the other day, right? It's like, I've been using it.
Thanks.
So all of the case races that you're running, you would not want to run out of soda pop before that occurred. So you will always err on the more side of beer. This is conservative. The same way, you're always going to estimate, well, the slab has a certain strain, or the concrete has a certain strain, let's reduce it a little bit. We don't know if it's true, but we know it's bigger than this number, for sure. So we're always safe. And so that's what it is. So this is, when we hear about this in the news all the time, but we need to trust the science. Well, science is one thing. It's very nice philosophy and everything else. But engineering is how things get done, right? Engineers are responsible for the outcome. So I keep asking people who say you want to take all these wild steps for climate change. I'm happy with that. Who's responsible if it's wrong? Because a lot of the models, remember at the beginning of this COVID-19 thing where there were going to be 2 million dead this year? And that's because of some of the assumptions that were built into the model. As they refined the model, they found out that those assumptions, some of them were not valid. It's still something to be concerned about and something to take precautions over. But that's why a reasonable person running a model was getting a very high number. And then it's like the weather forecast. They run 25 models. One of them says it's going to be 15 inches of snow. The other ones all say it's not going to snow. Guess which one leads the news? Right? Because the consequences of it snowing a lot and you not being expecting it is bad. Consequences of no snow, when you forecast a lot, they just look dumb. They seem to be impervious to that. They just go like, oh, well, we do that one. All right. So the Whitney stress block is not true. We know it not to be true. But we know it's conservative. We know it's whatever it is, it's bigger than that. And so this is what we call a hidden safety factor. It's inside the assumption. Okay? So we've got our two things, and then we can say, well, C prime is equal to T, which means that AS FS is equal to 0.85 F prime C AB. Then we have another equation. If we were to take the beam and cut it in the middle, in order for there to be a balanced moment, there has to be an externally applied moment. That's what's causing it to sag. The beam has to have an internal moment that's the same size to resist it. And if it can't handle that moment without failing, then that's our ultimate limit state. And so we have this force, C prime, and it's equal to 0.85 F prime C AB, and it can be thought of as a single force acting at a depth of A over 2 from the top of the beam. Down here, at a distance D from the top of the beam, is our tension force, AS F sub S. If we take the moments about point A here, capital A, we have our force C prime. What's the lever arm acting on that moment? For a force that passes through A, what moment does it cause at A? Zero, right? Lever arm is 0. This force here, the tension force, is acting at a depth D minus A over 2 from point A. And so our internal moment is given to us as A sub S, F sub S, multiplied by D minus A over 2. And these are our two important equations. The first is that C prime is equal to T. The second is what our internal forces are, our internal moment is, rather. Okay? And so if we do that, we will find that we can develop a model. And that model looks like this. Okay, must have lost a page. T is equal to C prime, which means AS F sub S is equal to 0.85 F prime C AB. Now, I can get the area of the steel from a drawing, right? I can look at it, or I can pick a bar, I can find out what the size is. B is the width of the beam. If I'm just doing an analysis, I'm looking at someone else's beam. That's all, I can measure that, right? F prime C and Fy, or F prime C, compressive strength of the concrete, that's a given as well. So the only two things that I don't know by looking at the drawing is A and F sub S, right? So let's rearrange our little equation. We're going to say, well, this is easy. Now we can rearrange this, and we have A is equal to A sub S, the stress in the steel, divided by 0.85 F prime C B. That's pretty cool. Still have two equations and two unknowns, or one equation and two unknowns, right? So that presents a bit of a problem. And our analysis method is going to rely on this equation and the second equation. That is that the nominal moment is equal to A sub S, F sub S, D minus A over 2. We don't know what M sub N is, so I just added another equation. So I got two equations, but I added another unknown, so now that's three unknowns and two equations. Still not working for us so good. But what if, I don't know, what if I just said the steel was yielding? If I said that the stress in the steel, F sub S, is equal to F sub Y, then I know what F sub S is. The only unknown I have up there is A and M sub N. Pretty cool, huh? So my method is going to be as follows. Number one, I'm going to get all the details from the drawing. I'm going to get B, and I'm going to get D, and I'm going to get F prime C, and I'm going to get F sub Y, and I'll get H. What else do I need up there? That's it, right? Oh, F sub Y, I got it. So then number two, I'm going to assume F sub Y is equal to, the stress in the steel is equal to the yield stress. Okay? So that's an assumption. And why do I like that assumption? It makes the math work. Is it true? How the hell should I know? I don't know if it's true or not. But I can check, right? Because if the strain in the steel is greater than the yield strain, then it has to be that the stress in the steel is the yield stress. And that's the purpose of you guys working on your assignment and the ties and the different strains, is to find out why, when it goes across the yield strain, it continues to strain at a constant stress. We're going to make that assumption. After we make this assumption, it's the easiest thing going. A is now equal to A sub S Fy over 0.85 F prime CB. I know all of those things, so it'll give me A. And then the nominal moment capacity is equal to AS F sub Y D minus A over 2. I know all of those things too. So I can very quickly calculate my moment. Then I need to do what? To get here, I said, yeah, sure enough, I'm just going to assume the steel's yielding. What do I have to check? Am I full of shit or not? Did it really yield? So I can do that, right? If you recall, I know that C, I'm going to check the assumption. I know that C is equal to A divided by beta 1. How come I know that? Because that's the definition of A. And then I further know that the strain in the steel is equal to 0.003 D minus C over C. Remember I get that from my triangles? Right? This is the strain in the steel. This is D. This is the strain in the concrete, which at failure is 0.003. In compression, this distance is C, and this distance is D minus C, and the strain in the steel divided by D minus C is equal to the strain in the concrete divided by C. Right? I didn't have to pull a rabbit out of a hat. At no time did my hands leave my arms while I was doing the calculation. Right? It's all just a big assumption. Yes, sir.
Is that C equals A over B?
A over beta 1. See, the beta has a long tail. We hardly ever see Greek letters, but now we have so many awesome, cool hurricanes creating construction opportunity for resilient housing. There's people who come back and say, oh, we'll build the same clapboard structure because, it's only been destroyed 3 times. What are the chances number 4? So that's the people in California. You build structures that are hurricane-proof and fire-proof. It's not that complicated. Guess what you use? Reinforced concrete. That's right. Houses are nicely insulated. You can put them up on stilts if you have to. But do you know how long a forest fire has to burn in order to damage the concrete? A lot longer than it could burn. You'd have to be throwing fuel at it. Concrete doesn't even care what's going on until it gets up to about 900 degrees C. Anybody read Ray Bradbury? Fahrenheit 451, the temperature at which paper ignites. It's about the temperature at which wood ignites. It doesn't get much hotter than that. 450 degrees is pretty hot, Fahrenheit. But 900, that's really, 900 C, that's really hot. So, and the concrete will then just start to powder at the surface. And the best part is, you'll see physical changes that let you judge whether the concrete is acceptable or not from 10 feet away. You can remain socially distanced and say, see those brilliant white areas right there? That's not so good. See that area that turned kind of pink? Yeah, that's better, but it's still crappy. And the other stuff that looks normal, that's perfectly fine. If we get a chance, sometime this semester, I'll bring you some pictures of what fire damaged concrete looks like. You often say, well, this is where the fire started. One of the ways to do that is to watch where the temperature was the hottest, and then you can follow it from the concrete. So, this is beta 1. I think we've gone past hurricane beta, right? Everybody knows the Greek alphabet, alpha, beta, gamma, delta, right? Heard of it. So we got at least one. There's more of them creeping in yet today. So, beta 1. And so long as the strain in the steel is greater than the yield strain, which is 0.002, then the assumption is valid. And if it's less than, then the beam is inadequate. And that's the solution. What's the capacity of the beam? It's not adequate. There are methods of solving these problems by iteration to find out what the strain in the steel must have been. And as much as I like doing hand calculations, by the time you're down through 5 or 6 hand iterations, you're kind of sick of doing it. So one day when we have 10 minutes in a class and we want to start a new topic, I'll show you how to do that. Okay, it's done with a computer. You guess, then you refine your guess as you're going along until you converge to a solution. So it's pretty fascinating to do, but we're going to stop at that point. If the strain in the steel is less than the yield strain, that means the steel didn't yield at failure. And what kind of failure is that? If it fails by the concrete crushing, a compression failure. And do we like compression failures? No, we do not. We are afraid of them. So, when we have things that we're afraid of, how do we usually handle that? If you want to encourage a behavior in society or discourage a behavior in society, how do we do that? Let's say, I don't know, what's one of the behaviors we don't like in society? People speeding on cars. What do we do to people that speed? Give them a ticket, right? We make it cost them money. So what we need to do is rig our code not only to say, thou shalt not have compression control beams, but to make it so expensive that you wouldn't want them, because you can say, I'm going to violate the code, I'm going to deviate from the code, because I'm a professional engineer and I can do so. Of course, my insurer doesn't know why, but he just had a very cold chill go down his back, right? That's taking on risk. Now, I might know what I'm doing, and that's fine. If I know what I'm doing, nothing bad will happen. But I might be a maniac. That's why they only let certain kinds of nerds become professional engineers, right? The kinds that don't have any humor and that like algebra. I've told you the story of my daughter coming down on a Saturday morning. Dad, what are you doing? Well, it's like this puzzle here that, it's n equations and n plus 1 unknowns. And so rather than play around and guess with it, I'm writing a parametric equation for the straight line that represents the family of solutions. What you going to say? Dad, it's Saturday. Yeah, are you doing that for work? Well, it's kind of a fun mental exercise. She's your age, right? She's a sophomore this year. So she's like, Dad, you need to get a life. All right, well, that ship sailed a long time ago. All right. So this is what we know, right? We know concrete is going to fail in compression at a strain of 0.003. And at that point, if the strain in the steel is less than the yield strain, then we get a sudden collapse, a rapid failure. If the strain in the steel is greater than the yield strain, or equal to the yield strain, then the stress in the steel is the yield stress. If that occurs, then we are going to start to see yielding occur. And yielding is the bars are going to start to stretch, and they'll stretch a lot. Not quite enough, not quite what we want, right? So we have three conditions. The first condition is the strain in the steel is less than the strain of yield when the concrete fails. That's compression control, and we do not like it. We also have number 3. The strain in the steel is greater than the yield strain, and that's tension control. We like that. And then we have what will become useful for us, an engineering condition. Engineering conditions mean something that probably never happens, but is useful to study. And that is, the concrete crushes just at the moment the steel starts to yield. So that it's yielding and crushing right at the same load. We call that the balanced condition. The structure is in balance. And that's going to be very useful for us to have that concept. So balance is right at the line. If you go a little bit more steel, you're in tension and compression control. If you do a little bit less steel, you're in tension control. So the balance condition we'll use later on. But, let's suppose that, I don't know, the yield, the strain in the steel is 0.0021. Okay, so it's yielding, but it's not yielding very much. And what we're relying on that concrete to do is to be yielding and past the past the tensile strain capacity of the concrete so that the cracks open wide and that you see them clearly as to what's going on. Since we don't have that condition readily, we don't want it to strain a little bit, right? We want it to strain a whole bunch so you go like, holy shit, look at that beam, we better get something underneath it, it's going to fall down. And have the time to do so. So we're not going to use 0.002 when we're designing. We're going to use 0.005. And this is the two conditions we have where we're straining. If the strain in the steel is above the yield strain, but below 0.005, we call that the transition zone. And if it is greater than 0.005, that's tension control, because now it's really straining. Okay? So up above, those are the scientific statements. The definition of transition and tension, that's set up by people. People that know what they're doing structurally, which hopefully will be everyone who's designing a structure, right? But that's not always the case. So we're going to like to be in tension control, and up until this semester, I would have taught you how to design, when we go to design, in the transition zone, because it used to be allowed. But the new code came down from Mount Arafat or wherever it comes down from, and they have decided that you can no longer have anything in the transition zone. It used to be okay if you're 0.004, but now you can't design there at all. You still may analyze a beam and find it in the transition zone, but you can't intentionally put it in the transition zone. Okay? So what does the transition zone mean? How are we going to give people speeding tickets if we don't like what they're doing? And the way that we're going to do that is we're going to have a philosophy in the code that takes into account a resistance factor. A resistance factor is a discount. We'll refer to them as phi factors all the time. So there's another Greek letter, phi. So you can
The weird looking A? Oh, I see.
see down below?
Yeah.
A resistance factor is a factor less than 1 that says, well, if our capacity is 10, let's just assume it's 8. Because it's 10, but if we assume it's 8, we can design, then we don't need to worry. And so our phi factors are going to be set to control what people are doing in their beam design. So we said that tension control, the strain is greater than 0.005. We like that, right? We're going to say, hey, strain's greater than 0.005. That is totally awesome. Good job. We're going to give you 90% of the beam capacity in your analysis. But if you're a problem child and you want to be in compression control, that's fine. Compression control beams are already more expensive because they have more steel in them. So we're going to take 35% of the strength away. We're going to have a phi factor at 0.65, which means that your beam has to be even bigger than it was. So you can do it, I guess, if you have to, but we're not going to rely very much on that beam because we don't want to get close to the edge and have it fail in compression. And in the transition zone, we have a sliding scale for phi. And you missed this on Tuesday. I couldn't find my notes, so I had to derive it from first principles. There's a straight line. Greater than 0.005, it's 0.9. Less than 0.002, it's 0.65. And in between, the phi factor is 0.65 plus 0.25 multiplied by the strain minus 0.002 divided by 0.003. And what that does is that's the equation of that straight line. So do you see how we use the phi factor to control how much risk we're taking? That's the resistance factor. Some of you took steel. I think do you do LRFD steel design? So you knew what this was already?
We've been talking about it the past couple of class periods.
Good. This is so much easier for concrete, right? Steel has all these crazy phi factors everywhere. That's it for tension or for bending. So that's the first half of a philosophical movement referred to as load factor resistance design. So if those are, do you need to back up there? I can always tell by the cries of pain. So that's a load and resistance factor design. We have the resistance factors. That is a number, less than 1, that we discount down the strength for. Conditions we know we understand well, tension control, a little bit of a discount. Things we don't like very much, compression control, a lot of a discount. Either way, we're reducing the strength of the beam so that we can design using the reduced strength beam, and then we'll be okay. We'll have a safety factor built in. That's the first half. All set to, can I swap it?
Oh, yeah.
Okay, everybody okay? The second half is load factors. A load factor is the quantity greater than 1 that we use to increase the loads. In other words, we're going to take a load that is that we know well, and we'll gross it up a little bit. And then we'll have a load we don't know very well. We'll gross that up even more. We'll look at different load combinations. And all these load factors and load combinations come from yet another document. The American Society of Civil Engineers, document 7, which controls loads. And in that document, we define the loading based on how important the building is. If you have, if you have an event that causes an extreme wind load, hurricane, residential houses, then sometimes they don't do so well. What's the building you don't want to take a chance with? Hospital. Anything else? School. Police department, right? Anything that if there's a disaster going on that you would like to be still functioning, you use a higher load factor. And so we have design codes for the types of loads that go on. And we have several types of loads. Have you done dead and live load in steel? So what's a dead load? Right? And a live load? Right. So the carpet is and me jumping up and down, live load. Very good. We have some other loads too, right? We've got wind and rain, snow, and then earthquake or seismic loads. So we're afraid of all these, and if we go to the ASCE 7, there's all kinds of combinations. And then what we'll do is say, well, this is a university, so I believe, I'd have to look it up, but I believe that it's a 50-pound dead load and a 60-pound live load is the requirement for all these buildings. A hospital might be 100 pounds dead load and 150 pounds of live load, which means that for a given structure, the hospital will be beefier than the school will be. And then residential might be 25 pounds live load and 45 pounds dead load. Or sorry, 25 pounds dead load, 45 pounds live load. And I can look it up in SCE 7 if anyone wants to see what those are. I can find them for you. There are exemptions. Agricultural buildings, buildings that are not going to be regularly occupied by people, can be less safe than those that are occupied by people because, let's face it, those pigs are dying one way or the other. Right? Hopefully, I understood, was anyone in the Twin Cities this morning? I understand they had a horse trailer flip over on 94? I don't think any of the horses were killed, but that's my wife reporting it, so I don't know. So things happen, right? So you have to be prepared for them. The most common equation that we're going to see, which gives us the maximum load, is 1.2 times the dead load plus 1.6 times the live load. So we're grossing the loads up, we're taking the resistance from where it is, we're discounting it, and then we're designing as though that was what was really going on. So all you have to do is have the moments caused by the loads, or the shear caused by the loads, or any other force caused by the loads, resisted by the discounted resistance, and you have a built-in safety factor. Working stress, which is the way we used to do design, is we'd take the loads without factoring them, and then we would say we're going to use a safety factor of 2, so we're going to take the strength, the capacity of the resistance, and divide it by 2. And that gave us a nice, safe number. But it's, of course, it was one size fits all, right? And so this is much more flexible. It saves on materials. It saves on construction costs. It's a better way of doing things. So this is where we're going. You'll notice we're still doing hand calculations. And in a lot of cases, simple structures are still built by hand calculations. So the next step in the code is going to, the code allows you, but does not restrict you to using other models, other methods for analysis. And we'll talk a little bit about that. Did you cover any structural analysis in statics? Your favorite course, right? Did you look at frames and how moment frames work? Cool. So I'll be teaching you how to do that. It's really fun. It's really fun, right? Because I wouldn't lie to you. I mean, this stuff is really fun too. So that gives you my standard of really fun. So our LRFD is a philosophy. Increase the loads, decrease the resistance, then design like those are the real loads and resistance, and everyone will be happy. So we covered a little bit new ground, right? We know what the balance condition is. We know what transition control is. And we formalized our analysis method. What's the best way to learn how to do these analyses? Is it hearing me talk about them and make bad jokes? What's the best way? Let's do some analysis. All set? Do you want a 5-minute break? Then we'll come back and we'll do some analysis.